Welcome back everyone. In this lecture, we will see some more applications of group action. So, in the last lecture, I gave proof of this Cauchy's theorem. So, let us go through the statement again. So, this is very important theorem for finite groups. Okay. So, if you take G to be a finite group, okay, let G be a finite group and let P be a prime number such that P divides the order of G. So, then this number of elements, okay, or let us look at all those elements G in G such that G power P is identity. This number of elements in this set, this is exactly congruent to 0 modulo P. Okay. So, this is what we proved. So, recall, so the way we proved, we constructed this group H, we took it as the group generated by the cycle 1 to P inside SP, and then we took G, the group as, okay, sorry, the group as H and then the set as the following set. So, you take all tuples G1 etc. Gp from G power P such that the product of this G1 etc. Gp is identity. So, then we saw that H naturally acting on X by permuting the coordinates, and then the fixed point subset X power H. So, this is nothing but having one-to-one correspondence between this the set that we are interested in. So, with this set. So, this is X power H is nothing but those tuples G etc. G P times such that G in G and G power P is identity. So, this can be naturally identified with the set that we have, those G in G such that G power P is identity. Okay. So, from this we concluded that the cardinality of H is naturally congruent to the cardinality of X power H modulo P, because the group H is P group, and we observe that the cardinality of X is nothing but the cardinality of G power P minus 1, and that proved that this number is actually congruent to 0 modulo P. So, this P divides this number. So, that forces that, so cardinality of X power H is congruent to G modulo P. In particularly this number, the number of elements of G such that G power P is identity is congruent to 0 modulo P. This is what we prove. So, as I said before, one can prove this using induction as well. Okay. So, you can reduce the proof to first of all abelian groups. Okay. Once you reduce the proof to abelian groups, so then you can actually use induction on the number of elements of the group to prove this result. Okay. Or straight away also you can verify for the abelian groups. So, let us see how one can actually go about it. So, to approach this problem, okay, we can use the class equation. Okay. Recall what is the class equation. The class equation says the cardinality of G is nothing but the cardinality of the center plus summation the cardinality of the conjugate classes that are having more than one element, which is exactly going to be the cardinality of G divided by the cardinality of the stabilizer Gx, which is the centralizer of X in G, where X comes from some particular indexing set lambda 1. So, note that suppose if you take this equation, okay, since P divides the cardinality of G, okay, in case P divides any of these subgroups. Okay, so if P divides Cg of x, the cardinality of Cg of x for some x in lambda 1, then what happens? So now we are just using induction, okay, to reduce the problem to finite abelian groups. So by induction you can assume that all subgroups that are having smaller than the cardinality of G satisfy this property. That means Cauchy's theorem is true. Okay. So now how this lambda 1 is defined? For x in lambda 1, we have the property that the cardinality of Cg of x is strictly less than the cardinality of G. So in particularly in case this P divides this cardinality of Cg of x for some x in lambda 1. So then by induction, okay, then by induction we have element of Cg of x having order p. Okay. So this is actually some weaker version of Cauchy's theorem, but later we will see this will be equivalent to this, but let's not worry about it right now. So we will actually prove that there are elements of G of order p. So this is what we will prove now. Okay. So now by induction we can actually conclude that Cg of x having order p. Now Cg of x being a subgroup of G, so then our theorem is true for G. Okay. So this actually completes the proof for G by induction. So in particularly what we can say, we can just assume that okay, P does not divide for all x in lambda 1. Okay. You can just safely assume P does not divide Cg of x for all x in lambda 1. Okay. So now look at this equation. The cardinality of G is nothing but cardinality of G divided by cardinality of Cg of x times cardinality of Cg of x, and this is true for all x. Okay. In particularly for x in capital lambda 1, with this assumption P does not divide Cg of x, that means Cg of x, the cardinality of Cg of x is relatively prime with P, but P divides R of G. Since P divides R of G and P does not divide Cg of x, so that forces that P divides R of G divided by this cardinality of Cgx, cardinality of G divided by the cardinality of Cg of x. Okay. So that is immediate from this equation. This is just a Lagrange's theorem. So that means whatever is there on the right side, this sum, okay, all the numbers that appear in this sum, they are all divided by P. Okay. So that is what we are getting. So recall the cardinality of G is nothing but cardinality of the center plus summation the cardinality of G divided by cardinality of Cg of x, where x comes from lambda 1. But all these numbers are divided by P by our assumption. So this entire number is divided by P. So in particularly the cardinality of G is congruent to cardinality of the center modulo P, but P divides cardinality of G. So that means the cardinality of the center is divided by P. So that means P divides the order of the center, but the center is abelian group. Okay. So this implies okay, P divides the cardinality of the center, and note that the center is abelian group. Okay. Suppose if you know this fact for the abelian group, then by induction you can complete the fact. Okay. So in some sense using induction you can reduce your problem to abelian groups. That is what this class equation says. Again class equation also corollary of our group action. So, this proof is also in some sense uses group action. Now, if you are working with abelian group, then if you go back to our previous argument, then there is no issue with this argument at all, because you can take again this group H which is generated by the cycle 1 to P and make it act on this G power P. Okay. So, G power P now being abelian, this product if you take it to be identity, there is nothing to check. Okay. SP itself acts on G power P. If you take this particular subset capital X, on which also SP will act, because the product of GI is identity. The order in which you write the product is does not matter whenever G is abelian. So, when G is abelian, we have SP acting on capital X. So, this is our capital X. So, our capital X does not change, but the group you can enlarge to bigger group. Okay. So, then you can look at all the fixed point elements. Okay. Then you can see that that will corresponds to the elements G in G such that G power P is identity. Okay. And that would say that, so this is still true for abelian groups. But unfortunately, okay, so because we are all working with only subgroups here, okay, capital G is a group and center or CG of X, all of them are subgroups. So, you have to actually collect everything together to prove that the number of elements of number of elements G in G such that G power P is identity is congruent to 0 modulo P. So, you have to group them all together. There could be some intersection and so on. So, that leads to some complication in proving the cardinality is congruent to 0 modulo P. But if you want to just to prove that there exist elements of order P, then this proof actually just does the job. Okay. So, here the advantage, like I said, you can enlarge the group and then you can actually go to this very big group SP, you can make that act on X. But of course, once you are going to restrict that action to H, you want to apply everything for H only, okay, not for the SP. But I am saying you have this bigger group acting, so you can restrict and then look at this action. There is nothing to prove, okay, when you deal with abelian group. Okay, this actually kind of gives another proof of Cauchy's theorem. Okay. So, now we will actually get back to some general group theory and then we will see that again some applications of group action in general groups. Okay. So, now once we know Cauchy's theorem, we can immediately prove the following thing. So, it is very important to understand groups of order small, groups of small order. Okay. So, I would say at least up to group of order 10 you should know the complete classification. Okay. For example, if you start with the group, okay, so the cardinality of G is 1, it is just identity, 2 it is cyclic group of order 2, 3 being prime, it is group of order cyclic group of order 3. Okay. And 4, so P square which is 2 square, so it must be abelian. Okay. So, I will leave it to you to prove the following. Okay. So, if group is order 3, then G is just isomorphic to Z modulo NZ. Okay. If group has order 4, so this is something I will leave it to you to verify. If it is group is as order 4, then G is abelian, that we have already proved. So, G in particularly isomorphic to Z modulo 4Z or Z modulo 2Z cross Z modulo 2Z. So, this is the only possibility. If it is 5, since 5 is abelian, so then you can see that G will be isomorphic to Z modulo 5Z. So, now we have group of order 6. Okay. If you take group of order 6, So, you already know two examples of group of order 6. So, one is Z modulo 6Z, another one is S3. So, there exists non-abelian group of order 6, that is S3, and there is abelian group of order 6 which is G modulo 6. Note that this is same as isomorphic to Z modulo 2Z cross Z modulo 3Z, because 2 and 3 are being relatively prime. So, this Z modulo 2Z cross Z modulo 3Z will be cyclic group which has exactly order 6. So, it will be isomorphic to 6. So, we will prove that these are all the only groups up to order 6. So, these are all only order 6 groups, and of course, up to isomorphs. Okay. I will only prove the of thing. So, I will leave it to you to verify. Okay. So, if G is abelian, then order of G is 6. So, that would imply G is isomorphic to Z modulo 6Z. Okay. So, this is again corollary of Cauchy's theorem, because if G is abelian and has order 6, so 6 can be written as 2 into 3. So, you can have order 2 element, order 3 element, because G is abelian, both must commute. So, now using this 2 element, if you take the product, the order should be the product of the order, because 2 and 3 are relatively prime. So, that will actually tell you there exists element of order 6. So, this is again application of Cauchy's theorem. So, now as a corollary of Cauchy's theorem, we will prove that S3 is the only non-abelian group of order 6. Okay. So, this is a result. So, what it is? It is a simple corollary of Cauchy's theorem. Suppose you have a non-abelian group of order 6, then that must be isomorphic to S3. So, that means you have to find out some some set that has exactly 3 number of elements, and then we have to say that this group naturally act on that set. Okay. So, let us prove this. So, how one can prove this? Let us call that group is G. So, the cardinality of G is 6. Okay. So, now using Cauchy's theorem, you can find some element A which has order 2, and then there is element B order 3. So, this is just by Cauchy's theorem. So, now you have these 2 elements. Now, you can see that AB cannot commute, AB cannot be BA. So, check that if AB equal to BA, okay, this is something I am leaving you to check. In case AB equal to BA, so then the order of AB is going to be 6, and that would imply G is isomorphic to Z modulo 6, which is a contradiction. Okay. So, that means AB should be not equal to BA. So, now look at this conjugation. Okay. Look at this subgroup H, which is identity. Okay. So, let us write it as E, identity and A, generated by A. So, this is subgroup of G of order 2. So, now if you look at this subgroup, claim is this cannot be normal inside G. So, not normal. Why? Because we can take conjugate of A by B, look at B A B inverse. So, if it is normal, then this has to be inside H. So, B A B inverse, then either has to be identity or A, but in both cases we have issue. If B A B inverse is identity, then that would imply that okay, A equal to identity, which is contradiction. P A B inverse equal to A, that would imply that B A equal to A B, which is again contradiction, because A B and B A do not commute. This is what we have observed. So, that means both cannot happen, this cannot happen. So, that means this cannot be there. So, that means H is not normal in G. But G naturally acts on all the cosets of H. Okay, G acts on this G modulo H via this left multiplication. So, define this tau where you take x and then send it to tau x. What is tau x does? It takes G modulo H to G modulo H, and then it takes, for example, GH to XGH. So, this is action that we have already verified. Okay. So, we have produced now, you can see that order 3 set. Okay. G modulo H has exactly cardinality of G divided by cardinality of H, which is exactly number of elements are 3. Okay. So, that means by fixing some order on this G modulo H, you can identify S G modulo H with S3. Okay. So, now look at this map tau and then like just check what will be the kernel. The kernel of tau is going to be, so those x in G such that tau x is identity on G modulo H. But what is the meaning of tau x being identity? That means x G H should be G H for all G in G. So, that is what it means. By taking G identity, you can see that x is in H because x H is exactly H. Okay. So, that implies the kernel of tau is subgroup of H, but H has only 2 elements, either kernel is full or proper. Proper means it has to be trivial. So, this forces that the kernel is either trivial or capital H, and it cannot be capital H because capital H is not normal, as H is not normal in G. Okay, that forces that the kernel is just trivial. So, if kernel is trivial means what? G is embedded inside S3. Okay, it is injective map, but S3 has order 3, G has order 3. So, this injection must be isomorphism. So, that proves that G must be isomorphic to S3 when G is non-abelian group of order 6. Okay. So, this proves there are only 2 groups of order 6, one is abelian which is cyclic G modulo 6, and one is non-abelian which is S3. So, this is very important corollary of Cauchy's theorem. Okay. And we can also get such informations about like some subgroups of G. Okay. So, when we use different actions and so on. Okay. So, let me do one more important result. Okay. These are about subgroups of G, and I am just trying to demonstrate how powerful is this group action. Okay. By taking various different actions, you can see that you can prove so many results. So, this group action is somewhat unified. Okay. So, this is the power of abstract algebra or the abstractions. So, once you abstract things by applying to specific situation, you get so many results. So, let's see this another corollary of group action, which is very interesting corollary. So, let's start with G being, again let's take G being finite group. Okay. H and K, they are subgroups of G. So, now what I want to do, I want to look at this Hk, which is by definition the product of elements of H and K. So, we know that this is just a subset of G. So, this Hk is just a subset of G. So, this can be subgroup if and only if Hk equal to Kh, that is something we verified. So, we want to prove that we can compute the cardinality of this Hk. Okay. The cardinality of Hk is going to be cardinality of H times cardinality of K divided by cardinality of H intersection K. So, this is such a nice result about the cardinality. So, this is something you can get it from again group action. By appropriately choosing some groups and sets, you can prove this. So, let us take what is the group? Group you take it to be the direct product of H and K. So, this is just a direct product, this is your group. I am going to just outline and I will leave it to you to check. So, what is your set? So, your set is going to be G itself, okay. Your set is G. So, this is the set. Now, what is the action? H cross K acts on G as follows. You take the tuple and take some element G, you just send it to this conjugation, okay, the double coset thing. Hk dot G is Hg K inverse. So, verify this is indeed group action, okay. I am not going to verify. So, now if you look at the orbit, what happens to the orbit? Orbit of identity, because the group is your set, okay. G is your set, E is inside your set X, which is G, okay. For the identity, if you look at the orbit, you can see that this is going to be exactly H identity K inverse, where H is coming from H, K is coming from K, but K is subgroup, okay. So, this can be rewritten as H K inverse, H in H, K inverse in K. So, which is exactly Hk, okay, because Hk is same as Hk inverse, because K is subgroup. So, orbit of one single element is nothing but Hk. So, if you are interested in computing the cardinality of this orbit, so this is exactly the cardinality of the Hk. So, this is going to be cardinality of your group, which is the cardinality of H cross K divided by the stabilizer of this identity, the stabilizer of this identity inside your H cross K, okay. But what is the stabilizer? You can just work it out. The stabilizer of this identity inside H cross K is going to be those elements H comma K inside H cross K such that H E K inverse is supposed to be E. But what it is? It is exactly H comma H, okay, H comma K, let us put it this way, H cross K, where H equal to K. You can see that this has natural one-to-one correspondence with H intersection K. So, using this you can immediately conclude this is cardinality of H, cardinality of K divided by cardinality of H intersection K. Okay. So, by looking at this very specific action of H cross K on this particular set G via this, you can conclude that. So, the cardinality of Hk is nothing but cardinality of H times cardinality of K divided by cardinality of H. So, this also can be proved using some elementary group theory, okay. Maybe you can try to prove this. I will leave it as exercise. Use some elementary group theory arguments to prove this, okay. So, this you can take it as exercise, but using group actions I just demonstrated how to prove this, okay. So, I will stop here. I will continue in the next class with much more important applications of group actions. So, namely Sylow's theorems and so on. And once we prove Sylow's theorem, then we will also see various applications of Sylow's theorem in finite group theory, and in particularly we will use that those theorems to classify some groups of orders, groups of small order, okay. So, we so far classified groups of order up to 6, Okay, these are all this, here is the thing. We will do this for other orders as well. Okay, I'll stop here. Thank you.